All right, so we're going to start with number 8 on this video. A few applications here. It says you're playing tennis with a friend. The path of the tennis ball after you return a serve can be modeled by the function y equals, and then we're given this beautiful function right here, where x is the horizontal distance in feet from where you hit the ball, and y is the height in feet of the ball. What is the maximum height the tennis ball will reach? So let's make sense of this, and we're going to do this through this fabulous drawing, of course, I'm going to make. Here's a little tennis net. That's a net. And let's draw the tennis court here just to kind of try and make sense of this problem. So here's my court. This is me playing tennis here, or you. I guess it says you, so you're playing tennis. And here's your racket. So they serve it over, and you're going to hit the ball back. So here goes the ball, right? Again, the x-axis is the horizontal distance. So if you think about it, right, it's moving in that direction, hopefully towards the other side of the court. And then the y value is telling you how high the ball is actually going as it moves into the other court. So if we're thinking about every point of this graph, the first part, again, is like the horizontal distance that it's moving towards the other side of the court. And every output is then going to be like the height of the ball. And again, both of those are in feet. So when we're asked to find the maximum height, remember maximum means vertex. And if this is in standard form, the way we find that vertex is negative b over 2a. And then we plug that in to find the y value. And specifically, it wants the maximum height. So we actually need to go all the way to the y value to find this. So let's start here. It looks like our a value is negative 0.005 and our b value is 0.17. So we're going to do negative b, or in other words, negative 0.17 over 2 times negative a. Okay. When you simplify that in your calculator, you get negative 0.17 over negative 0.01, which is 17. So when it's moved 17 feet, then we're looking at plugging that in to figure out what the y value would be there. So we take our original equation, and everywhere there's an x, we're putting in the 17. Okay. When you go ahead and calculate that, you should end up with 4.445 feet. So that's what we'd be looking at there. Number 9, create a quadratic equation in vertex form, then in standard form for a function that has a vertex at negative 3, 4, and passes through this point. So let's start with our vertex form. Again, remember vertex form has the h and the k, so we've got minus h plus k. So as soon as I see it tell me that this is the vertex, I label that h and k, and I go ahead and put it in the equation. So I have x, negative 3 in here would make positive 3. And plus 4 on the end there. Again, they give us another point as our solution value that we can use to help find that stretch or that shrink a value. So this would be like y is equal to a. We go ahead and put the x in here, negative 1 plus 3 squared plus 4. And then we also want to put the y in. I apologize, I didn't do that. So we want to put the y value over here where it goes. So I'm going to put 12 there. So we get 12 is equal to a, negative 1 plus 3 is 2 squared, and we have plus 4 there. If we keep going, 12 is equal to, and we want to get rid of the exponent, so 2 squared is 4a. We then have plus 4 here. So we'll subtract 4, and we end up with 8 equals 4a. Divided by 4, a is equal to 2. So our final vertex form, we go ahead and put in that a value. So vertex form would be y is equal to 2 parenthesis x plus 3 squared plus 4. Now if I want to write it in standard form, I need to take that vertex form, and we practice doing this, but we're going to basically break up that x squared so that we get x plus 3, remember there's 2 of them. And then we go ahead and we multiply that out. So we get 2, we get x squared. If we're foiling this, we get 3x and 3x, which is 6x plus 9. And then we have that positive 4 in the end. We distribute the 2 into those parentheses. So 2x squared plus 12x plus 18. We still have that plus 4 on the end. So our final equation in standard form would be 2x squared plus 12x. We combine the like terms to get 22 there on the end. So we've got a vertex form and a standard form. Number 9, so we're given that from a top of a 4.5 podium, a sea lion jumps into a large tank of water. The height of the sea lion at any time is modeled by this function right here, where h of t equals 0 represents the surface of the water. So it looks like they've drawn us a little graph here, and it looks like we have a seal sitting here at about 4.5. He's going to jump into the water and then come back out. So we definitely know it's going to start at like 4.5. Now it says draw a graph of the function. So either we can tell where the vertex is by using the negative b over 2a, or we can use the calculator. If I was using the negative b over 2a, then I would have 5 divided by 2 times my a value, which is 0.5. That would equal 5 over 1, which is just 5. So I know that if I was drawing this graph, the x value of my vertex is 5. And then we would go ahead and we would plug that in. So if we plug that in, then we get h of 5 is equal to 0.5 times 5 squared minus 5 times 5 plus 4.5. And again, if we simplify that, we get 8. So we can plot that point over 5 down 8. And we know that it will continue to kind of move through that. Again, you can use your calculator to help you plot some of these points as well. We are going to find, when we find the x-intercepts, that when, remember, x-intercepts occur right when the function is at 0. But again, this one's about interpreting the function. So if you use the calculator to graph that one, that's just fine. We just want to be able to kind of interpret what this means. Now we don't know how far the seal comes out of the water once he goes down and then back up, so I'm just going to have it stop right there, but it could continue. He could pop right out. This says state the minimum height that the sea lion reaches. So again, that minimum height is down there at the bottom, or in other words, the y value of our vertex. So the minimum height would be 8 feet underwater. And it asks us, when does he reach that? Well, if we look at our time there, which is the x-axis, he reaches that at 5 seconds. So he's under there for a little while. Identify the x-intercepts. So if you look at our graph, our x-intercepts, right, are 1, 0, and 9, 0. And it asks us to describe the meaning. So if you're describing the meaning here, and we're just understanding that the seal is going to enter the water after 1 second, and he's going to resurface at 9 seconds. So you would just state something along those lines. The water at 1 second and resurfaces at 9 seconds. D says identify the time interval for which the sea lion is going in an upward direction. So this is, again, if we're going in an upward direction, that would be like an increasing interval, right? And it looks like we're going anywhere from 5 seconds to 9 seconds, or just where the time is greater than 5. And again, that's the increasing interval. So if we were giving it a name. All right, number 10 is asking us to create another quadratic equation. So this one's in intercept form this time, and then in standard form. So remember, intercept form, I'm going to start with its basic. This is the one with x minus. So if we go ahead and we plug in our intercepts, remember intercepts are the values where y is 0. So we would have y is equal to a. We would put in x minus 3 and x minus a negative 5, which makes plus 5. We then are given that solution point or extra point to help us find the a value. So if I come over here and say, well, if I put 24 in for the y, and everywhere there's an x, I'm going to put a 1 in. We get 24 is equal to 1 minus 3 is negative 2, and 1 plus 5 is 6. So 24 equals, remember parentheses mean multiplication, so 6 times negative 2 is negative 12, times a is negative 12a, and we divide by negative 12. Yikes. So a is equal to, it looks like negative 2. So if you come back over here and put that a value in, you get negative 2x minus 3 and x plus 5. So there's our intercept form. Now again, if we want to write it in standard form, I'm going to write this off to the right-hand side. We've got x minus 3, x plus 5. And remember, if we want to distribute this, we can just go ahead and FOIL that. So we get x squared. We get positive 5x minus 3x, which combines to 2x, and then we get negative 15 there. And then we go ahead and distribute that negative 2 into each piece. So negative 2x squared minus 4x plus 30, because we've got a negative times a negative. That would be our standard form. From each of these forms, we can identify the vertex. So this says state whether the quadratic function is in intercept for vertex or standard form. Then we'll find the vertex, axis of symmetry, and the range. So first of all, if we look at this one, this is the one with the h and the k, so this one would be known as vertex form. Okay. To find the vertex in vertex form, again, we like this one because it's easy to find from that vertex form. That's just that h and that k. It then asks us to find the axis of symmetry. Remember, the axis of symmetry is the x value of the vertex. It goes right through it. And then lastly, it wants us to find the range. So we look out front of the equation and see a positive 2, which just means this graph is opening up. So our range goes from the y value of the vertex up to infinity. Number 12, again, if we look at this one is solved for the intercepts. So this one is intercept form or factored form. If we want to find the vertex of this one, remember that if we know where those x-intercepts are, wherever they are, the vertex is halfway in between them. So we're going to find our solutions here would be negative 3 and positive 5. So we do 5 plus negative 3, and we divide that by 2 to find halfway in between. That would be 2 over 2, or in other words, 1. So it looks like our x value of our vertex is 1. Now, just like standard form, we go ahead and plug 1 into our equation for the x values. So I'm going to put 1 here, minus 5, and 1 here, plus 3. If I simplify that, that's 2 times negative 4 times positive 4. So 2 times negative 16 is negative 32. Okay. Again, this one is going to go, axis of symmetry goes through the x value of the vertex. And then for our range, we look out front. It's a positive 2. It's opening up. So we use that y value of the vertex that we found, and it's going up to infinity. Number 13, again, this one's in standard form. So this one has the a, b, and the c value. On this one, we use the negative b over 2a when we find the vertex, right? We know this one as standard form. So this is standard form. Again, negative b over 2a, so that would be negative 6 over 2 times 3. That's negative 6 over 6, which is negative 1. So as my vertex, the x value is going to be negative 1. And we plug negative 1 in to then figure out what the y value would be. So it looks like we'll have negative 1 squared is 1, so that's just going to be 3. We get a negative 6 when we multiply those two values. So 3 minus 6 is negative 3 minus 1 is going to be negative 4. So we're going to have negative 4 here. Again, axis of symmetry goes through that vertex for the x value. And this one, again, has a positive 3 for its a value, so it's opening up. So we're going from that negative 4 y value up to infinity. Very good. And to finish out this page, which of the following functions do not have x-intercepts at 9 and negative 3? So the easiest ones to kind of eliminate on this one are the ones in intercept form. This guy would have intercepts at positive 3, because that's a solution, and negative 9. So this one, oh, we already know it's B. That one does not have intercepts at negative 3. Notice the one right below it, that one would have intercepts at negative 3 because its solutions are negative 3 and 9. And you could continue to factor each of these and you'll find that each of those would give you those same intercepts. But because it says not, we can stop there.